Today everyone, we will introduce the third law of thermodynamics, but first, we need to know what is thermodynamics. Thermodynamics is a branch of physical science that deals with the relations between heat and other forms of energy, such as mechanical, electrical, or chemical energy, and by extension of the relationships between all forms of energy. The word thermodynamics comes from the Greek word thermi, which means heat, and dynamics, which means power. The third law of thermodynamics is concerned with the limiting behavior of systems as the temperature approaches absolute zero. Most thermodynamics calculations use only entropy differences, so the 0 point of entropy scale is often not important. However, we discuss the third law for purposes of completeness because it describes the condition of zero entropy. The third law states that the entropy of a perfect crystal is zero when the temperature of the crystal is equal to absolute zero. According to Purdue University, the crystal must be perfect or else there will be some inherent disorder. It also must be at 0 Kelvin, otherwise there will be thermal motion within the crystal which leads to disorder. One version of the third law states that it would require an infinite number of steps to reach absolute zero, which means you will never get there if you could get to absolute zero. It would violate the second law because if you had a heat sink at absolute zero, then you could build a machine that was 100% efficient. In theory, it would be possible to grow a perfect crystal in which all of the lattice spaces are occupied by identical atoms. However, it is generally believed that it is impossible to achieve a temperature of absolute zero, although scientists have come quite close. Therefore, all matter contains at least some entropy owing to the presence of some heat energy. Absolute zero, the lowest temperature that is theoretically possible, is an entropy of thermodynamic property that is measure of a system's thermal energy per unit of temperature that is available for doing useful work.
In order to avoid confusion, scientists discuss thermodynamic values in reference to a system and its surroundings. Everything that is not a part of the system constitutes its surroundings. The system and surrounding are separated by a boundary. For example, if the system is 1 mole of a gas in a container, then the boundary is simply the inner wall of the container itself. Everything outside of the boundary is considered the surrounding, which would include the container itself. The boundary must be clearly defined so one can clearly say whether a given part of the world is in the system or in the surroundings. If matter is not able to pass across the boundary, then the system is said to be closed, otherwise it is open. A closed system may still exchange energy with the surroundings unless the system is an isolated one, in which case neither matter nor energy can pass across the boundary.
Hello everyone, I'm Lloyd Sanchez and I will introduce the absolute zero theory. Absolute zero is the lowest limit of the thermodynamic temperature scale, a state at which the enthalpy and entropy of a cooled ideal gas reach their minimum value taken as 0 kelvins. All systems in thermodynamic equilibrium at absolute zero have vanishing entropy. This principle is called the Nernst heat theorem or the third law of thermodynamics. It is impossible to reduce the temperature of any systems to absolute zero in a finite number of steps. On the absolute temperature scale, which is used by physicists and is also called Kelvin scale, it is not possible to go below zero, at least in the sense of getting colder than 0 Kelvin. At 0 Kelvin, the particles stop moving and all disorders disappears.
The concept of absolute zero as a limiting temperature has many thermodynamic consequences. For example, all molecular motion does not cease at absolute zero. Molecules vibrate with what is called zero-point energy, but no energy from molecular motion, that is heat energy, is available for transfer to other systems, and it is therefore correct to say that the energy at absolute zero is minimal. Any temperature scale having absolute zero for each 0 points is termed as absolute temperature scale or a dynamic scale. In the International System of Units, the Kelvin scale is the standard for all scientific temperature measurements. Its fundamental unit, the Kelvin, is identical in size to the Celsius degree and is defined as 1 over 273.16 of the triple point of pure water. The temperature at which the liquid, solid, and gaseous form of the substance can be maintained simultaneously. The interval between this triple point and absolute zero comprises 273.16 kelvins. The lowest temperature achieved in experiments has been 50 picokelvin. pK, 1 pK equal to 10 minus 12 K.
Good day, everyone. My name is Norshad Ginda, and I will introduce the entropy, the measure of a system thermal energy per unit temperature that is unavailable for doing useful work because work is obtained from ordered molecular motion. The amount of entropy is also a measure of the molecular disorder or randoms of a system. The Nernst heat theorem asks that the entropy change for any reaction of pure crystalline substances goes to zero as the temperature goes to zero. Subsequently, Max Planck suggests that the entropy of reaction goes to zero because of still more basic phenomenon. The entropy of every crystalline goes to zero. As the temperature goes to zero, further investigation then showed that Planck formulation fails for substance. Carbon monoxide, in which crystalline solid does not become perfectly ordered at the temperature goes to zero. The Lewis and Randall statement refines the Planck formulation by recognizing of that non-zero entropies will be observed at absolute zero for solids that are non-crystalline, and for crystalline solids that are not perfectly ordered. The Lewis and Randall statements also makes a choice implicit also in the Planck formulation. Of the 0 point for the entropies of chemical substances, namely some crystalline state of each element and at absolute zero. This choice ensures that at any temperature greater than zero, the entropy of every substances will be greater than zero.
Good day everyone, I will introduce the Gibbs free energy. In thermodynamics, the Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum reversible work that may be performed by a thermodynamic system. At a constant temperature and pressure, Gibbs free energy, denoted G, combines enthalpy and entropy into a single value. The change in free energy, delta G, is equal to the sum of enthalpy plus the product of the temperature and entropy of the system. Delta G can predict the direction of chemical reaction under two conditions, constant temperature and constant pressure. If delta G is positive, then the reaction is non-spontaneous, i.e. an input of external energy is necessary for the reaction to occur. If it is negative, then the reaction is spontaneous, occurs without external energy. Gibbs energy was developed in 1870 by Josiah Willard Gibbs. He originally termed this energy as available energy in the system. His paper published in 1873, Graphical Methods in Thermodynamics of Fluids, outlined how his equation could predict the behavior of systems when they are combined. This quantity is the energy associated with a chemical reaction that can be used to do work, and this is the sum of its enthalpy H and a product of the temperature and entropy S of the system. This quantity is defined as follows: G equals H minus Ts1, or more completely as G equals U plus PV minus Ts2, where U is internal energy, P is pressure, V is volume, T is temperature, S is entropy, H is the enthalpy. Gibbs energy in reactions. Spontaneous is a reaction that is considered to be natural because It is a reaction that occurs by itself without any external action towards it. Non-spontaneous needs constant external energy applied to it in order for the process to continue, and once you stop the external action, the process will cease. When solving for the equation, if the change of G is negative, then it is spontaneous. If change of G is positive, then it is non-spontaneous. The symbol that is commonly used for free energy is G, can be more properly considered as standard free energy change. In chemical reaction involving the change in thermodynamic quantities, a variation on this equation is often encountered. Delta G change in free energy, delta S change in enthalpy, minus T, delta S temperature change in entropy.
Good day to all. I'm Alvin Paul Pabico and I will be the one to explain on how to calculate entropy. But before we start, let's discuss what is entropy. Entropy is a measure of a probability and the molecular disorder of a microscopic system. If each configuration is equally probable, then the entropy is the natural logarithm of the number of configurations, multiplied by Boltzmann's constant, which is S is equal to KB ln W. So for this topic, we are going to be using the formula S is equal to K sub B ln omega, where S is equal to entropy, K sub B is equal to Boltzmann constant, ln is for natural logarithm, and omega is the number of microscopic configurations. Let's now proceed on solving a sample problem. Find the change in entropy, where the delta S for the hydrolysis of urine. In this problem, they gave us the equation given the following entropy values. Since we have the standard entropies of each of these compounds, we can then use that by taking the entropies of formation of the products minus the entropies of formations of the reactants. So we start with the carbon dioxide. The entropy of the formation of carbon dioxide is 213.6, and we only have 1 mole of carbon dioxide, plus the entropy of formation of ammonia, 192.5. But we have 2 moles of that, so plus 2, suppose 2 times 192.5, and we're going to subtract that from the entropy of reactants. We have CO and H2, 2, and we've got 1 mole of that. So its entropy of formation is 173.8, and also minus the other reactant, liquid water, and its entropy of formation, 69.9. We total all of that, and we get the change of entropy. The standard change of entropy as 354.9 joules per K mole. That's all from me.
Boltzmann constant. Having dimension of energy per degree of temperature, the Boltzmann constant has a value of 1.380649 times 10 to 23 joule per Kelvin, or 1.380649 times 1016 erg per Kelvin. Natural logarithm. The natural logarithm of number is logarithm to the base of the mathematical constant e, where e is an irrational and a transcendental number approximately equal to 2.71, 82, 81, 82, 84, 59. Microscopic configuration of thermodynamic system that the system may occupy with a certain probability in the course of its thermal fluctuation. This distribution describes the probability of finding the system in a certain microscope. Example 1. So we have a list of equations here, but the one that is the most sustainable is this one where it says this free energy is equal to enthalpy minus the temperature times the change is entropy. So in this example, we have both delta S and delta S, so we were just going to substitute in it. So the delta H is a 180.7 kilojoules minus 298 times entropy. The entropy, you will notice, is in joules, not kilojoules. So we're going to convert that and we get plus 173.3 kilojoules. The significant feature is
Celsius, 173 Celsius, the question asked is this reaction spontaneous or thermodynamically favorite, and the answer is no. This is not spontaneous because the delta T is more than 0.
What is absolute zero and what happens to molecules when the temperature reach absolute zero?